That being said, I would like to welcome Dr. David Williamson to give us a talk on Galaxies and a Supercomputer. So please welcome him with a round of applause.
Okay, hey everyone. So I am Dave, and I am an astronomer. The people I work with, I work for those people, Southampton. I get paid for those people in Europe, which we're in technically. Alright, so who am I? What am I doing here? Okay, so obviously I'm not originally from England, even though I did live here when I was about 2 years old for a little bit. But I started my sciencey career in Wellington in New Zealand. I actually didn't start with astronomy. I started doing molecular dynamics stuff, so I started doing like almost chemistry. Did my master's in that, but I decided astronomy was cooler. So I moved to Canada, did a PhD doing galaxy kind of stuff in Halifax, Nova Scotia, which is kind of a nice little port city, actually a little bit similar to Southampton in some ways. Got married, my wife's Canadian, which is nice. We kind of figured that she's going to be following me around for my academic career, so I followed her in one of her dreams, and we went to South Korea for 1 year and did a little bit of teaching there at a primary school. South Korea is quite cool. It's pretty different to New Zealand in a few ways. Then I went to, the goal was to get back into astronomy, so I went to Quebec City and did what we call a postdoc, which is like a research position for someone who's already got a PhD but isn't smart enough to teach yet. So I did there, did more stuff in Galaxies, got a dog. It's a good dog. Brought the dog to England. This is my second postdoc position, where now I'm here. I'm actually doing research on active galactic nuclei, which is what Noel was talking all about, the bright supermassive black holes in the center of galaxies. Here, working at Southampton, got a baby, which is pretty good. Alright, so we've heard a lot about galaxies and what's inside galaxies. But what I'm going to talk about is how we build simulations, computer simulations of these galaxies to work out like how they evolve and what they do, and kind of to try to interpret the observations we see on the sky. So first got to see like what are the ingredients, what are the different bits of a galaxy that we want to try to model. So a galaxy is made up of, you've got gas, in this picture of this random galaxy that I took off the internet. You got some gas there. The dark brown stuff is sort of like dusty lines of gas. The little red pops are like little bits of ionized gas from like stars that have turned up and ionized the gas fairly recently.
Okay.
Cool. The stars. It's not a galaxy if you don't have stars. All the like blue and sort of white stuff are stars. I think everyone knows what stars are. There's dark matter. Nobody knows what dark matter is, but it's pretty important. You get the wrong answer if you don't have it, so you got to have something, even if it's not dark matter. So you have these things, and all these things we actually kind of understand the equations for how they work at a fundamental level. So those are the equations that, again, just from some random page on the internet, these are the Navier-Stokes equations, which are the equations for the gas. We also understand stars pretty well, that people have been researching stars for a long time, so we have a lot of understanding of those. And even dark matter, the cool thing about dark matter, and this is why we love dark matter, is that you don't actually need to know what dark matter is very much. Because it turns out that a lot of the models aren't super sensitive to it. You can have fairly general equations that don't really care what dark matter is made of and still kind of get pretty similar-ish answers. So we have all these sort of equations. So what's the problem? We have these equations, let's just solve them. Just, find someone who's really good at math and just do it. I said math. I spent too long in Canada. Maths, there you go. Alright, so the problem is that we aren't that good at maths. Apparently, if you are good enough at maths to solve this equation, the Navier-Stokes equation for how gas behaves in space and in general, that's $1 million. You know, there are prizes out there for this sort of thing, and to encourage people to try to solve them, and no one's done it yet. And it's a pretty good motivator, and so what do? What we got to do is we've got to break the problem down, and that's what we call an algorithm. And this is an algorithm that I'm sure everybody loves, long division. So this is probably the first algorithm that anyone has, that most people encounter in their life. You don't usually think of it as an algorithm, but it is an algorithm. You take a problem that's too hard to solve in one go, and you break it down into little steps, which are easier to solve, and then you go through those one at a time, progress in kind of a loop until you get to the final answer in the end. And that's essentially what we're doing with computers when you're trying to simulate a galaxy. So we take something like a galaxy, which is super complicated, and we kind of zoom in to like a really small piece. And if you look on a really small scale within a galaxy, it starts to not be quite so complicated anymore. I mean, there is stuff in there that we're sort of blurring over, but it's on a sort of small enough scale that we can actually kind of start to solve these equations decently. Even if we're using approximations, the approximations start to get pretty okay if we can go into sort of a small enough scale. So what we do is we chop our galaxy up into lots of little pieces, and each one of those pieces is small enough that we can work out what does the gas and the stars and the dark matter do within that little chunk of the galaxy. We can chop it up into cells or particles. And then we can work out how much what will happen to that little chunk of the galaxy over a very small amount of time. And then we do it again. We say what will happen to that little chunk of galaxy over another small amount of time. And if we do that enough times, over enough different little chunks of the galaxy, we start to build up a picture of the evolution of the galaxy as a whole. Now, oops, that's not supposed to start yet. Okay, so this sort of thing, it really is important for these, for you to use really small chunks of time and of space. So what I've got here is a simple example of a simulation. This is a simulation of, let's say, a planet going around a star, something like that. In this, I've set up the velocity, so it should go in a nice, perfectly circular orbit. And then I run the simulation to see what happens. Whoops. It's close. It goes kind of in a circle, it's not quite right. And the issue there is that the jumps in time were too big. And all the sort of like approximations we make only really work if you're making really small jumps in time, each time that you model the planet moving forward a step. So we can make this again with smaller chunks and get a little bit more accurate. And if you get smaller jumps again, hey, kind of looks right. So we have to really chop up our galaxies into very small pieces of space and very small pieces of time if we're going to model them with any amount of accuracy. You could say that we need a very high resolution in order to do that, if anyone didn't get that already. Alright, so this kind of illustrates why we need computers, because, okay, so let's say you have 1 million cells, you chop it up into 1 million bits. Let's say you've got 10 equations that you have to solve for each one of these little chunks of galaxy, and you do it like 1 million times stepping forward in time, something like that. So that's 10 trillion steps, which is quite a few. And of course you can break that down further, that each one of those equations you're actually doing quite a few different mathematical operations in there, and what an actual computer would do is even more than that. So the actual number might be a lot bigger than that. So that's quite a lot of stuff to do. So what you need to do is use a computer. And so many years ago, people decided to use a computer, and that's what a computer was. A room full of people, mostly women actually, using adding machines and pen and paper and doing a whole bunch of calculations at the same time. So how would that work with one of these modern calculations? So let's say you got your 10 million steps. Let's say you're quite good and you can do like 5 seconds for each step. So that's 1.5 million years. That is prohibitively long if you want to have a return on your grant, even if you have a good few people working on it at the same time. So, I mean, of course you can go ridiculous with this. So we've got 10 trillion people, 10 trillion equations you're doing. It takes a line for equation. A page in the book has maybe 32 lines in it. The book has like 64 pages. So you've got 500 million books full of paper that you've been using. Apparently, if you look up the weight of paper in a book, it's about 80 grams per book. So it's about 400,000 tons of paper to do one of these things. You can look up what weighs about 400,000 tons. Empire State was one, apparently. There you go. So of course, we don't use an old-style computer as a room full of people with adding machines. We use electronic computers. This is actually not here. This is the Colosse supercomputer in Quebec City. And I think the nice thing about this photo is that it kind of illustrates what a modern supercomputer is. So you can see there's a whole lot of wires there. It's not one big machine. It's not just like you can take a computer take a program that runs okay on your laptop, put it on a supercomputer, and it will run 100 times faster. It doesn't work like that. What a supercomputer actually is maybe 1,000, 10,000, 100,000 fairly ordinary computers all wired up together with this networking stuff. And this is actually one of the core problems when it comes to programming these algorithms in order to solve these equations and do models for galaxies or anything. And this is the same problem that people do hit when they're doing weather or even like economics kind of type simulations and so on. So, because you're not just you're kind of having to spend have all these different processes solve the same problem at the same time. So you can kind of imagine a situation like doing the dishes. So imagine that you're doing the dishes, you're doing them by yourself, you have to wash all the dishes, you have to dry the dishes, you have to put them away. That's okay. Maybe you got someone comes along to help you out. They dry the dishes. Sometimes they're kind of waiting for you to finish washing a dish before they can dry it. So you've got 2 people working the job. It's not quite twice as fast, because they're kind of waiting for you part of the time. Then a 3rd person comes along. Maybe they help put away the dishes. But still there's kind of a bottleneck, because you can't really fit that many people around the sink. I mean, maybe you can get multiple sinks, but at some point, you end up with more people than dishes, and you're not really speeding things up. And this is kind of the type of problem we have in parallel computing, is that like you can't just throw more and more computers at a problem without thinking really carefully about how you're going to organize it. So we've actually got a little exercise here to demonstrate that. And I think that a puzzle is a good example, because a puzzle, you actually kind of need to coordinate with each other a little bit. So what we have here is, I think everybody, well, a large number of people have puzzle pieces that have been distributed around the place. This is, I think, is a fairly simple puzzle. So let's say that if it would take, if it would take like a few minutes for 1 or 2 people to do it, then maybe it'll take you guys, if there's a dozen or a couple of dozen people, sure, we can do it in a minute, right? So if everyone's got a puzzle piece, you could stand up. We have in the corner by the bar there's a nice open space. If you'd like to get together and as efficiently and quickly as possible put together this puzzle. Go. Okay, let's see what we're doing. 5, 4, 3, 2, 1. Okay, this all people are too keen to finish this puzzle. Okay. So, we did it? Almost. Okay. So, this is a good illustration of why, again, why we can't just throw, a million CPUs at a problem and have it come out well. Because if you notice, like, most of you were just spending the whole time waiting in line, waiting for your chance to compare. Because you can't just solve a puzzle by yourself. You need to fit the pieces in with everyone else's pieces, so you need to see where they are. And it seems like a lot of people, they went in, put in their one piece, and then that was it. You only were working efficiently for like 1%, if less, than that whole time. And I think I might have also seen something that also comes up in parallel computing, is you have a few people at the front who kind of manage everything, where everyone else kind of does nothing. And this is again, is the same sort of thing. And this is something that happens in these simulations. Because if you're doing simulations with gravity, gravity is a long-range force. So you can't just, so one side of the galaxy is gravity affects the absolute other side of the gravity of the galaxy as well. So you have all these forces at long distances, and you really need to have every part of the galaxy know at least something about every other part of the galaxy. It's an interactive thing. You need knowledge of everything else, and so it's really something that's kind of a bit tricky to sort out, and there are lots of clever ways to do it. But to sum it up, this is an old saying about. This is about programmers. What one programmer can do in 1 month, 2 programmers can do in 2 months. And I think this applies that if you don't design it well, what one CPU can do in 1 hour, 2 CPUs can do in 2 hours. Okay. So that's about how it looks to sort of like try to design and program these things. What are the actual computers we run on? So I showed you Colossus, which is in Quebec. We of course have our own supercomputer at Southampton. This is a shared one between like pretty much the whole university. It's called Iridius. This one has, oops, that's not the button for the laser. There we go. This one has about 12,000 processors in it, of course. So you can run 12,000 different things at once. We actually tend to share that. You have to like submit jobs, and you don't get to use all 12,000 at once. But if you split it up, 100 to one person, 1,000 to another, you're still using quite a few things, and you really need to think about how you are using all those different threads at the same time. Now, if you're kind of wondering, if you want to buy one yourself, you can actually buy like a little supercomputer. It's kind of getting down to sort of reasonable prices. This one isn't 12,000 processor cores. It's about 200 or 196 exactly, and that's the actual price of it. It's about 40,000 American dollars. So we're kind of getting to the point where you can get a supercomputer that's cheaper than the guy you're paying to program it. So that's it's kind of getting about that kind of order of thing. So I don't know, I can't remember that. What does it actually look like for us to use a supercomputer? Well, there's a good depiction from a movie that you might have seen. It's wrong, but it's a good movie. This is The Martian. I'm not going to criticize this movie because I'm sure Ridley Scott knows more about movies than I do. But this is a real supercomputer. It's the Pleiades supercluster that NASA has. This is Donald Glover sitting in the server racks with his laptop plugged in to a supercomputer, and it comes up, calculations correct. Yeah. Okay, no. So what it looks like for using a supercomputer looks like this. This is my desk, this is my laptop, that's my coffee mug. We have the internet. You don't need to go to a supercomputer. I don't even know where some of our supercomputers are. You just log in, you submit the job. You don't need to be at your desk, of course. You know, you can work from home. So yeah. So that's a little bit of like the general overview of how this type of thing work. But what about me in my personal research? I'm just going to show you a very quick little animation that I've made in my research. So one of the things, I'm interested in a few things, but one of the things I've been looking at lately is dwarf galaxies. Francesco talked about there's spiral galaxies and elliptical galaxies which are generally like the bigger galaxies. On the other end of the spectrum, you have very small, sort of like fluffy little galaxies that we call dwarf galaxies. And these are two dwarf galaxies that happen to be close enough to see with the naked eye, if you are lucky enough to live in New Zealand. And they're only visible in the southern hemisphere and only when it's dark, which is really nice if you're in my parents' backyard. But you got the small Magellanic Cloud and the large Magellanic Cloud. They call them Magellanic Clouds because Magellan was one of his expedition was one of the first ones to go down from Europe to the southern hemisphere and like make charts and stuff, and they saw these two clouds in the sky and they named them after him. But these are two dwarf galaxies that are going around the Milky Way. And as they go around the Milky Way, they are actually interacting with each other and interacting with the Milky Way. That their gas hits the gas of the Milky Way, their stars are pulled by the gravity of the Milky Way, and they do all sorts of things to each other. And so I've been running simulations to see what kind of things happen to these galaxies, to a galaxy something like one of these Magellanic Clouds orbiting around something like the Milky Way. And so I've got this little animation here, and what this animation actually shows is what we call metallicity. Metallicity is basically the heavy elements that are thrown out by supernova and stuff like that. So what we'll see is as the simulation runs, there's going to be a whole bunch of stars and supernova going off in this galaxy, and that's going to throw all this like enriched stuff into the galaxy. And you'll see that sort of blowing out for a while. And then at the end of the simulation, it sort of runs out of gas, and you're just left with this sort of like enriched, it runs out of fuel, and you're left with this sort of enriched gas at the end that all just nicely settles down. And the camera, just to be melodramatic, is spinning around the galaxy, which kind of makes it hard to see what's going on, but it looks cool. So I don't do this in like research conferences. Yeah, so there we go. Ooh. And you can see like the big like booms of like star formation setting off supernova and stuff. And then it kind of settles down and you have like this concentration in the middle. Yeah, let's do that again. See little bubbles appear and so on. Okay, so that's a little tour around some of the basics of like what it means to do simulations of galaxies, and just a quick example of one that I've done. Questions?
To ask what kind of data you need for these simulations. Do you need like there's a number of data that you need? What kind of?
Do you mean how much RAM do we need, or like what input we need?
What input you need?
Okay, yeah. So the question is, what kind of input data do we need for these simulations? It very much depends on what type of simulation you're doing. Some simulations, and this is kind of more what Francesco is interested in, is we start at the beginning of the universe, essentially. So we do cosmological simulations, and then we have to look at parameters we think that the primordial gas and dark matter had, and we let that collapse into galaxies and so on. I tend to look at individual galaxies. So what my initial data is, I kind of look at what are the typical properties of these types of galaxies. So my example is I look at Magellanic Clouds, and so we look at what's something that kind of looks like a Magellanic Cloud. We don't model them in extreme detail. They tend to start out, we tend to have things very symmetric and that let the simulation make other stuff. So it's not like this is a Magellanic Cloud, it's something like a Magellanic Cloud. But it is based on like the general properties, like how the stars differ with radius, that kind of stuff. So,
are you able to validate those simulations in any way? Have you worked out whether they're showing you anything sensible?
yeah, so the question is how do I validate the simulation? So yeah, that is a pretty critical thing that we do have to do, and constantly we have to compare simulations with observations. It can be tricky because you can't see an individual galaxy evolving. So what you usually have to do is kind of do it in a statistical way. And one of the best ways is if you make a large sample of galaxies, you can say, do the patterns of brightnesses and types of stars and types of enriched elements match what we see in observations. That kind of thing.
Are there any other questions? Don't be shy.
Are you ever surprised by observations that you've made and then
Well, yes, you are surprised. Usually it's when you made a mistake. Because you type in something wrong, you think you do something slightly wrong and your galaxy explodes. That happens too often. Sometimes you find things that are surprising. Actually, the very first galaxy simulation that I know of done on digital computers found a surprising result. And what they did is they said, okay, a galaxy is a bunch of stars moving in a circle around the center. So they put all these stars in perfectly circular orbits around the center of the galaxy. And it turned out it was wildly unstable. It collapsed into a spiral arm, and they're like, oh cool, this is where spiral arms came from. Then they came back to it a year later, ran it for a bit longer, and the spiral arms flying apart. And it actually turns out that you can't have stars on perfectly circular orbits. They need to have a little bit of randomness to it, because that randomness sort of washes out any instabilities. And so that was like one of the very first simulations by Hole in the 60s-ish. Happened to find something completely not what they expected. And these days, there's usually someone who's done similar simulations to what you've done, enough that you don't often find things that are completely outrageously not what you expect, but you do still get surprised. How do I calculate the randomness to make a galaxy stable? Okay, so this one is, there's a number, it's called the tomb rate parameter. Basically it is, there is a nice little physical theory that's fairly simple, and you can say that based on the density of stars and how the gravitational potential changes and that kind of stuff, you can work out exactly what velocity dispersion you need, what dispersion of random velocities you need. So it actually comes out fairly simple mathematical thing.
Are you worried about artificial intelligence overtaking your ability very soon?
Yes, the question is AI going to make me obsolete? So AI hasn't. So there are things where machine learning works really well. And we have colleagues who use machine learning for looking at farming huge data banks to find supernova and that kind of thing. I don't think it works terribly well in this situation, because the thing about machine learning is it's an iterative process. You have to run a simulation and then sort of like check how well it goes and go back to it. And you have to do a very large number of simulations for that to work. These simulations might take a week to several months to run. And at that level, like, you can't really have an automated iterative thing to come up with your answers.
In the example that you modeled, roughly how many parameters or variables did you have to include in the model to generate those data?
Oh, so how many parameters did I include in that model? It kind of depends what you mean by parameter, because there's like initial conditions, which is what the galaxy is to set up with. That's not really physical parameters of the, that's setting up what the galaxy is. We do have to set. There are some things that do kind of have to be tuned in terms of like how stars form and stuff like that. Some of these you can get, they are measured parameters, but they're still kind of plugged in there. I don't think I really have a good answer, because it depends very much on what you define as a parameter.
Thank you very much for the You guys did great. You almost finished the puzzle. That would have meant that he wasn't able to prove his point. Oh my God, what's that? She's cute.
Oh yeah.
Yeah, she's really cute. Right. Great. So thank you, David, again. And right, so now we have a few people to reword for the bingo. Yeah, so you will have to remind me about that.